Hello and welcome everyone. In this video, we will look at a problem related to vibration of a string whose ends are fixed at points x is equal to 0 and x is equal to 1. The variable that we are interested in is the vertical displacement of the string from the x-axis or transverse amplitude vibrations at position x and time t. The vibration of a string is governed by the 1D wave equation, and for this example we can assume v is equal to 1. From the boundary conditions we know that the displacement is 0 at both ends of the string, and the initial conditions specify that the displacement at time t equals to 0 is sine of pi x and its time derivative is 0 at time t equals to 0. We can use the second order time and second order space differences to approximate the derivatives, and assuming alpha is equal to dt squared divided by dx squared, we can get to this explicit formula. If we apply central difference formula to approximate the time derivative at time t equal to 0, we get ui at t equal to minus 1 is the same as ui at t equals to 1. Now, if we let n is equal to 0 in our explicit finite difference formula and we replace the value of ui at t equal to minus 1 with ui at t equal to 1 as obtained from the approximation on the initial condition, we get this formula for time step equals to 1. Now we know the displacement value at time step 0, and we can also compute the displacement at time step 1 using this formula. Then for time step 2 and above, we can use our main explicit finite difference formula. And the scheme is stable as long as delta t is chosen following the stability criterion, which in this case is v delta t over delta x must be less than or equal to 1. We also know the analytical solution of this problem, and we can solve the 1D wave equation using the explicit finite difference scheme and compare with the analytical solution. In this case, our numerical and analytical solution both agree. Another example of 1D wave equation is that we have a disturbance or seismic source at the center of a 1D medium and the waves propagate in both directions. Both sides of the medium act as a reflective boundary, so the waves perfectly reflect back with a polarity flip. In this case, we are using a second order time and a fourth order space approximation of the corresponding derivatives. With this, we conclude our video. Please try to expand this wave propagation to 2 dimensions and leave your questions or feedback in the comment section. Thanks for watching, and please don't forget to subscribe to my channel.